Hello everybody, my name is Peter Klapper, and in this video clip I want to discuss with you some absolutely fascinating features of biochemical pathways and how they are regulated or about certain regulatory networks, which makes them look very similar to actually electronic networks. And I think this is incredibly fascinating, because we do understand electronic networks, but when we are looking at something like sort of a metabolic chart here, with loads and loads of reactions that are happening at the same time in the cell, we are not quite sure really if we can totally understand what's going on. But it would be great if we could, because if somebody presented with a disease, we could more or less treat this like, if your PC doesn't work properly. We have all the information about the components in your PC and we potentially can fix it. And that is really an absolutely fascinating topic, in my opinion. When you take some very simple components together, for example, in an electric circuit, you have a resistor, you have a capacitor, you have got a little battery or something like that. You put these things together and then you get something out that is absolutely different to the individual parts. I'm sure this holds true for these very complex biological pathways, and actually it has a name. It's called an emergent property of this pathway. Emergent means that the sum of everything is very different to the individual components. And actually this is also how our brain works, or how we think the brain works. The brain is made up of individual neurons, billions of them, and each neuron can do only very limited things. It can fire or it cannot fire. But the combination of all these 80 billion neurons in your brain, that makes you, that gives you consciousness, that makes you solve the most complicated problems in, let's say, biosciences, that makes you fall in love and or hate other people. So this is an absolutely fascinating topic, and I try to, in the next few minutes, I try to discuss with you what simple regulation mechanisms we have. So one of the mechanisms that we have is a very simple negative feedback loop. So, for example, we produce the compound A, compound B is then converted into compound B, and compound B inhibits the production of compound A. And at the same time then compound B produces compound C, and so on and so forth. And we have what is generally called a toy pathway, but these toy pathways really are very useful in helping us understand what's going on. So how do we think this system will react eventually? What would be the outcome of a system like that? Now we can do a sort of a time course, and we have some modeling software that can do that. And what we find that when we choose the conditions correctly is that at the beginning we end up with a little bit of A, so low levels of A. B is high, but when B, let me go here. So when B gets strong, we've got lots of B present, it stops the production of A. And if A is stopped, then no B is delivered. The regulation is relaxed, more A is delivered, B is produced, B then inhibits the production of A. And what this looks like is a sort of the system. We see a little bit of oscillation here, so it goes up, it goes down, goes up, but eventually it finds a stable steady state. We have defined concentration of B and A at the end. So if you like, a negative feedback loop can stabilize a system. It can make sure that there is no weird things going on. It stabilizes the concentration of A and B. And that's quite important if we think about biochemical processes. We don't want, for example, our glucose levels to vary too dramatically, so therefore we have negative feedback loops in it. And a feedback loop is because it feeds back here, and it is negative because it shows inhibition. So what would be exactly the opposite of a negative feedback loop? It would be a positive feedback loop. So for example, A is produced, it produces B, and B then activates further the production of A. So B could be an effector of an enzyme that produces A in this case. So let's think about it. What could happen in a case like that? So we have this positive feedback loop, and the concentration of B has a positive effect on the concentration of A. So pause the video for a moment and try to figure out what could happen. Will we find a stabilizing effect? Now we can do some time course again. And what we find is something really interesting. If we start off with a low concentration of both A and B, we will end up in just a very low steady state point. It's very low, and basically the system doesn't respond. However, if we choose high concentration of A and subsequently a high concentration of B, what we see is that the system ends up in a high state. So if we start with a low state of A and B, we have a low output, a low steady state of both components. But if we have a high state, if we have high concentrations of A and B, we end up with a high level, with this level here. So that means our system really depends on the initial concentrations of the compounds that we are looking at. So we have here a biphasic system, a bistable. This is actually called a bistable system. It can have two stability points depending on the starting concentrations of A and B. Now, what do we get if we have something like that? So A is produced, and A inhibits the production of B. When B is produced, it inhibits the production of A. What is going to happen? Think about it, pause the video and try to figure out what happens. So, welcome back. Have you tried to figure out what we get in this case? Well, a really bizarre thing that happens. We get, again, a bistable system. Bistable system, but this time it is slightly different. If we start with a high concentration of A, we get a system that has a very low concentration of B. So that's this point here. Likewise, if we start with a low concentration of B, we end up with a high concentration of B. So we get this point. Again, we have bistability, but this time it discriminates, it differentiates which one is higher, A or B, and reacts accordingly. So this system is different, and you can see that from the time course, is different to our positive feedback loop, where we have behavior like that. The bistable system of a coupled negative feedback loop looks very different, but it actually again ends up in two different possible states. It can be either on or off, depending on the original starting concentrations of A and B. Now, what happens if we have a combination of negative feedback loops? If we have several feedback loops, so for example, A inhibits B, that should be inhibition, A inhibits B, B inhibits C, and C then inhibits A again. What do we think what will happen? Again, pause the video and try to figure out what could happen in, for example, a time course. Do you get it? Well, probably not, because what actually happens in a time course is an oscillating behavior of the three compounds. So A, that's the red line here, it goes up, goes down, goes up, goes down, and with a certain phase shift, we see the same for B, goes down, goes up, and for C, but they are all shifted slightly. Now, where would we find something like that? Well, we would find this, for example, when we want to initiate certain stages in the cell. So, for example, this one here, where we have high A, this could symbolize to the cell, go into S phase. So this is not just limited to metabolic networks. It can also work for genetic regulation. So go into S phase. We have these negative feedback loops where one gene product can inhibit the transcription or translation of another gene product. So go into S phase and then go down, shut off S phase when everything is done. So here we have this oscillating behavior. We also see that for certain metabolites, that, for example, you produce certain metabolites only during the night or during certain periods of the day, and then at other periods they are going down and show this really nice oscillating behavior. And that's something probably you would not have expected, because after all we have just feedback loops here. But depending on how you put these feedback loops together, we get very, very different behaviors, and sometimes behavior that we would not expect just by looking at these feedback loops. And that is what this emergent behavior is. Now, here is another really nice example of a more complex feedback loop, so of a metabolic pathway. So we have compound A is produced and it can go in direction B, or it can produce C. B is then converted into D. D can either, we have a branched pathway, D can either produce E or G. E is converted into F, G is converted into H. So far, so good. Now, let's actually see what happens, what would happen if we increased, just by sheer accident, if we increase the concentration of H here. What happens if we increase the concentration of A? What is the consequence for this pathway? Now, let's try to figure out. So H blocks the production of G. So H blocks its own production. So no more G is produced. And let's say we don't move on from H or F. So here we have a block. As a consequence, we would accumulate D here. So D would go up, and therefore we would channel everything into this pathway here, into the upper branch of that pathway. So we produce from D, we produce more E, we produce more F, and F shuts down this pathway here. So F shuts down its own production, like H shut down its production in the lower pathway. So what we get is an increase in D, and this D is further and further increased. So we get high concentration of D. Now D inhibits the production of B, of this part here. So no more B is produced. So D shuts off its own production here through B. So what happens? Now A increases dramatically because it is produced, but it can't use this pathway here. And therefore, if A is increased and it can't use this pathway, we would see that it goes down in this direction, and we would observe a dramatic increase in compound C. So by changing or increasing the concentration of H at this point, we see an effect on the concentration of C somewhere else in this network, just by including these three feedback loops. And again, this is a very, very interesting regulation that we find very, very often in metabolic pathways. The special thing here is that we have branch pathways. And if you basically change something in one branch, it will have an effect on concentrations in related, connected other branches. Here is a very interesting situation where we have a more complex element, just simply by two enzyme reactions, a kinase reaction and a phosphatase reaction. And what this actually leads to is a switch-like system. It's really a very, very interesting behavior of the system, just made up of, let's say, a kinase and a phosphatase, two enzymes that have exactly the opposite effect on the concentration of a protein and a phosphoprotein. And if we are working at close to the Vmax for both enzymes, we find that the system behaves like a very sophisticated switch. So if we have the ratio of Vmax 1 over Vmax 2, if that is smaller than 1, then we have everything in the form of the protein. If our ratio is larger than 1, then we shift everything over there. And just by changing very slightly this ratio of the two Vmax for the kinase and the phosphatase, you see just a tiny change here has a dramatic effect on phosphoprotein or on the unphosphorylated protein. So this is what puzzled a lot of scientists previously, how this works. Because it's a little bit like my wife earns the money and I spend it. So it's also sometimes called a futile cycle, but it's not futile. It is a regulatory element. It is a very interesting switch. And we can use these switches to do a little bit more electronics. So for example, if we have a system like that, where we convert E into D, like kinase here, and a phosphatase here, so here in this case, and we inhibit our enzyme. We inhibit it, so that's a kinase inhibitor. For example, what we see is that if the inhibitor is present, and we choose our Vmaxes accordingly, if the inhibitor is absent, let's do it this way. If the inhibitor is absent, if we have no inhibitor, then everything would be ending up in D. But if the inhibitor is present, let's call it 1 here, then we find that nothing ends up in D and everything is in E. So or D would be 0. So let me write this differently. So we would say D equals 1 and here D equals 0. This is actually, in electronic terms, this is what is called a NOT gate. We can check, is the inhibitor present or not? And if the inhibitor is not present, we get D as the output. If the inhibitor is present, we get nothing of D and everything is in E. And that is basically a combination of this zero order ultrasensitivity up here and an inhibitor that inhibits the kinase. We can go further. We can go, for example, into a system with 2 inhibitors. So here we have, and I just draw these arrows a little bit nicer. We have something like that. We have 2 inhibitors and we have 2 combined switches. And what we see is that if we don't have, let's say, if we don't have the inhibitor 1 and inhibitor 2 present, so if they are both 0, so then the reaction goes this way and in this way, and we don't have any A left. If we have only one inhibitor present, so inhibitor 1 is present, then we go that direction, we produce A, but since we don't have inhibitor 2 present, everything would end up in C. So A would also be 0. If we have it the other way around, if we have no inhibitor 1 present and inhibitor 2 present, it would be exactly the other way around. So we would go that way, we would produce A, but this A is then converted immediately into B. So again, we have 0A. So under which conditions would we get A? We would only get A if both inhibitors are present, and I indicate that with a 1. And in this case, we only get A if we have both inhibitors present. And that is, in electronic terms, an AND gate. We can make things even more complicated. We can do an OR gate. We need either inhibitor 1 present or inhibitor 2 present. And as long as we have inhibitor, one of the inhibitors present, we would get an output in terms of D3. So that's an OR gate. Here we had an AND gate where we had to have the inhibitor, both inhibitors present at the same time to get an output. Here we need only one inhibitor present to get an output. And you can see these are all electronic circuits, and or switches, NOR, NOT, AND. All these things are electronic circuits. And if you really want to look at these things in that way, you can basically say here's an electronic network. I don't know exactly what it does. It's probably a sort of a filter or something in a radio or so. And if you compare that to a biological network, they look pretty much the same, and they use similar principles of regulation. And that makes it really, really fascinating. Because, for example, my dad is an electronic engineer. And he just has to look at one of these circuits here. So if something doesn't work, he does a measurement, let's say here, he does a measurement here, and then he says, it's working or it's not working because this component here is not working properly. So we understand electronic networks very easily. Now imagine we had this knowledge about these really elaborate biochemical systems here, where we can say, okay, somebody presents with a certain disease with certain problems, metabolic problems, they have high glucose levels or low whatever metabolite levels, we could then say, okay, let's measure this point here, let's measure this point here. We see that the enzyme here in this point is not working as it should do. And this understanding of these biochemical networks, that is really fascinating, and that gives us incredible power. So with this analysis of these biochemical control systems, what we can do is we can do some mathematical modeling, as I showed you. We can do time courses, we can do visual modeling, so that we see what's going on. Does the system have a bistable state? And there is some really cool software out there. So for example, if you Google XPP Auto or JDesigner, you'll find that there is a lot there. We can look at mathematical concepts like graph theory, or in engineering terms, we can look at systems control analysis. What are elements that control a system, and how do they make a system behave? Because the big aim that we want to have is that if we can understand how the properties of a biological network can change and they can be manipulated, and we can do that by modeling them on electronic circuits, then we can understand diseases and develop highly efficient cures for all sorts of diseases, like we can repair electronic networks. So I think this is an absolutely fascinating and really new field in old boring biochemistry, where we look not just at the different pathways and what's happening in these pathways, but actually what happens in terms of regulation, because that will give us the key to really deal with whatever disease there are. So I hope this makes sense, and thank you very much for